In this video, we're going to look at air resistance. We're going to take a relatively simple problem. We're going to have a block that just sits on a frictionless surface. It will start with some initial velocity, v0. It'll be affected by air resistance, and air resistance will follow what is known as Stokes' law, and that simply means that the force of air resistance will simply be directly proportional to the velocity and in the opposite direction. And what we're going to do is find the velocity, acceleration, and position of the block as functions of time. Before we do this, we're going to have to review a little bit of calculus. Now, some of you may not have had all of this, but all we really need to know is what an antiderivative and what a derivative is. And specifically, we're going to need to know what is the antiderivative of a function, namely 1 over x. And I'm not going to prove this, but when you do this in calculus, pay attention because you will need this. Namely, that the antiderivative of 1 over x is the logarithm of x. Because this is an indefinite integral, we have to add an integration constant c. The second function we're going to need to worry about is the exponential. And the derivative of the exponential, particularly e to the bx, is just b times e to the bx. And again, the antiderivative of that exponential function, so if I integrate e to the bx dx, the result is 1 over b times e to the bx, again, plus the constant of integration c. We will be using these three theorems from calculus, and I'm not going to prove them, but again, when you take this in calculus, make sure you pay attention because we will need those three basic facts. Now, the physics problem we're going to solve in the exact same procedure we have used before, namely drawing the free body diagram, picking our frame of reference, using F equals ma, applying the force laws, which will be Stokes' law, and now the mathematics we're going to do will be calculus, and that'll be the focus of this particular problem. Will be solving a differential equation. So first, the free body diagram. There's no tension forces to worry about, and there'll be no friction because the surface will be frictionless. Instead, we will have air resistance to worry about. We do still have gravity pulling down, and we still have the normal force pushing up, and as I mentioned, the drag force pushing in the opposite direction. And those are the only three forces acting on the block. We also do have to pick a frame of reference, and we're going to do something very conventional. We're just going to attach our frame of reference to the ground and put the x-axis parallel to the ground and the y-axis perpendicular to it. Now we're going to just apply F equals ma to get the equations of motion. On forces acting on the block in the x direction, that is just the air resistance, which will equal mass times acceleration. And the difference is here, we're going to represent the acceleration as the derivative of the velocity, which we haven't done before. And in the y direction, we just have the normal force and weight, and they have to add up to 0. This second equation will not be needed because the main reason we need the normal force is if we have friction, and we're going to assume our surface is frictionless and air resistance does not depend on the normal force. So we technically don't need the second equation. Now, the law we're going to use is Stokes' law, that the drag force is minus k times the velocity. And we can collect that together, so we have the force minus kv equals mass times acceleration, and acceleration is a derivative. Now we have a differential equation because the acceleration will depend on the velocity, or the derivative of a function will depend on the value of the function, and that is a differential equation. We're going to solve this differential equation by just collecting terms together, so we have all the velocities on one side. We're going to put everything else on the other side. So effectively, on one side of the equation, we put the constants, minus k over m, and the differential of time, dt, and we're going to bring the velocity over to the other side of the equation, so we have dv over v. We're going to solve this by just integrating both sides of the equation, because what we have right here is how a small change in velocity is related to a small increment of time. And we're basically going to add up all those small increments of time and add up all those small increments of velocity to get the overall velocity at a later time t. So we're going to integrate from time t equal to 0 to a later time t, and at t equal to 0, the block will have some initial velocity v0, and at some later time t, it'll have some other velocity v. And this is what we want to find, is what is the velocity at this time. So here we have minus k over m times the integral of 0 to t of dt. and that equals the integral of v0 to v of dv over v. So we have two integrals to evaluate. So first we're going to evaluate the integral on one side, which is just minus k over m times the integral of to 0 to t of dt. Well, that's straightforward, that the integral of dt is just t, and since it's a definite integral, it's evaluated at the lower and the upper limits. Well, the lower limit is conveniently 0. So the first integral just simplifies down to minus k over m times t. Now we're going to do the second one, which has a dv over v as the integrand. And there, what we're going to use is this form right here. It has the exact same form as the integral of dx over x, only I'm calling x v here. So it's dv over v, and that's just the logarithm. So our integral right here is just the integral of dv over v is the logarithm of v. This is a definite rather than an indefinite integral, so it's evaluated at the lower and the upper limits. That is the logarithm of v minus the logarithm of v0. And that is just the logarithm of the ratio of v over v0. We're going to set the two integrals equal to each other. So we have minus k over m times t equals the logarithm of v over v0. And we're going to solve this equation for the velocity v as a function of the time t. We're going to do that first by exponentiating both sides, raising them both to the power e. So this side right here just becomes e to the minus k over m times t. On the other side, we're going to have e to the logarithm of v over v0. Well, that's just a function and its inverse, so that just becomes v over v0. Multiply both sides by v0 and we get our first result. Namely, the velocity will equal the initial velocity times e to the minus k over m times t. And that's one of the things we were looking for. So we now have the velocity as a function of time. We can then take the derivative to get the acceleration and find the area under this velocity graph, or integrate to get the displacement. So first, to take the derivative, we simply take the derivative of an exponential. Well, as we mentioned earlier, the derivative of an exponential is just this. It's just the exponential times the constant. So here what we're going to do is simply take the derivative of this. We just take the constant b, which is minus k over m, bring that down, and it's e to the minus k over m times t. So there's our acceleration as a function of time. The acceleration is this constant, and it's negative, which we would expect because it's slowing down, times this exponential. So we now have the velocity and the acceleration. Now, to get the displacement, we're going to take the integral of the velocity as a function of time. And again, we're going to integrate from our beginning time, t equal to 0, and find out where it is at some later time, t. And here again, we're going to take advantage of the fact that here we have the integral of an exponential. And the integral of an exponential is this third equation right here. And it's 1 over the constant times e to the bx. And here we're going to have a definite integral, so we won't have a constant of integration. So here we have this is the constant I'll just take out of the integral. This is the 1 over b, which is minus k over m, times e to the minus k over m times t, evaluated at our two limits, 0 and t. And then we evaluate that, e to the minus k over m times t, minus this evaluated at 0, and e to the 0 is 1. And here I have a minus sign, and I'm going to simply distribute that minus sign out and say the displacement is just m times v0 over k times 1 minus e to the minus k over m times t. And there is our displacement as a function of time. So collecting them together, we now have our answers. V as a function of time is the initial velocity times this exponential. So notice it'll exponentially decay with time. The acceleration starts out with a negative value, and again, it exponentially decays with time. The position, we really calculated the displacement. The displacement is just x minus x0. I will take ourselves as simply starting at the origin, so x0 equals 0. So x is just this expression right here. This is now the position as a function of time. It is m times v0 over k times 1 minus e to the minus k over m times t. We can now check our answers and simply verify that t equal to 0, I plug 0 in here, I get my initial velocity back, and that's correct. If I let t get infinitely large, the exponential will eventually go to 0, and the velocity will go to 0, the block will stop. The acceleration at t equal to 0 is minus k v0 over m. Well, k times v0 is just the initial drag force, because that's just Stokes' law. The minus sign is that it's slowing down, so it's the force divided by the mass, and that is the acceleration. So this is the initial acceleration. As t goes to infinity, this number right here, this exponential, goes to 0, and the block stops, and basically, since it's not accelerating, it remains at rest, which should make sense. Eventually, air resistance will stop the block, and once the block is stopped, it will no longer continue moving. It will not accelerate anymore. The position is a little more interesting in that if I take at t equal to 0, I get 1 minus 1, which is 0, assuming we start at the origin, and in fact, it does have us starting at the origin. But as t goes to infinity, this second term goes away, but I still have the 1 right here, and x will go to m times v0 divided by k. And that is the limit as to how far the box will move before it stops. So this is the overall displacement of the box. Now we can take a look at graphs showing the velocity, acceleration, and position. So right here we have the velocity exponentially decaying over time. And here we have the acceleration starting at its initial value and exponentially decaying to 0 over time. And this is the position, which starts at the origin and asymptotically approaches its limit, which is m times v0 divided by k. Now note what we have just done is we have just re-derived the basic kinematic equations that we used under constant acceleration, and now we have a different set of equations to describe the position, velocity, and acceleration of an object, which is subjected not to constant forces, but rather to variable forces, and forces specifically that are directly proportional to the velocity. And that's what we were looking for, and now we have our answer.